Good morning, everyone. Hello. Welcome to today's webinar. Let's just give it a couple of minutes for everyone to join. As you know, today we're going to be talking about step-up transformers and the hidden costs of poor substation design. I'm your host. I'm Daniel Oliveira. I'm a member of the customer success team here at RatedPower. And maybe I'll make use of this time just to introduce myself shortly. I've been a part of the customer success team for almost 3 years now. And specifically, I work with Iberia and Brazil markets. We have the pleasure to optimize the usage of the tool for our clients. Let's just give a couple more minutes for everyone to join. And I also wanted to remind everyone that on July 9th, we'll have another webinar, this time focused on the latest updates of the tool, and will be conducted by our product owner, Juan Zamorano, from the product team, who will be guiding you through the latest updates on the software. Thanks everyone for joining. Again, today we're going to be talking about step-up transformers and the hidden costs of poor substation design in rated power and how we can solve these issues. Just a quick recap for everyone who just joined. I'm a technical advisor here at Rated Power. My name is Daniel Oliveira, and I specialize in the Iberian and Brazil markets. And today, this is our agenda. On the first half of the webinar, we'll be covering a little bit about the transformers and how we design them in substations and power stations in Rated Power. And on the second half of the webinar, we'll be facing some of the issues we typically see within our users, and we'll help you give the best optimization to your project and some tips to understand, for example, the calculations in the energy model or reviewing the documentation. Perfect. Well, let's start with the transformers. Just a little bit of context. I'm sure everyone here is well familiar with the concept. They are components that are used to transform the voltage level, and they're exploiting the electromagnetic induction phenomenon. How does it work? Well, as you know, a varying current creates a magnetic flux, and this, under good circumstances, for example, a core that allows better transmission of this effect. If we place two coils near enough, we will have a second current induced in that second coil. So this is basically the idea. Depending on the number of the coils, we'll also be able to control how we transform the voltage between both flowing currents. Something that I want to highlight is, for example, that these are affected by two main losses that are related to the different components of transformers. For example, the iron core is associated with the iron losses that will be constant and present throughout the whole time, whereas the copper losses are related to the Joule effect. So we will only be facing those when there's a flowing current. On today's webinar, we'll be reviewing how these losses impact the energy calculation, and I'll leave that for the second part of the presentation. I also thought it was a good idea to just remind everyone why we use transformers. As you know, this is just an example of the grid structure in our industry, where we have different generation sources, different levels of consumptions, and depending on the scale, we'll be transmitting this generation and this power in a different level. We can differentiate, for example, the TSOs, the transmission system operators, for higher voltage levels, and the distribution scale for our day-to-day homes, for example. This is a similar schema of what we see in rated power. It's a little bit of the structure that the program allows users to define. We will be, for example, inputting our PV modules, our structures, defining the type of inverters that we want to use in our project, And as we know, the generation occurs at low voltage. And finally, the grid operates at high voltage level in the utility scale. So in between, we find two transformers that step up first to a medium voltage and finally to a high voltage. Also, just wanted to remind everyone that we also can size a battery system, and this will also mean we find a transformer in this system. Why do we use transformers again? Well, again, the network and the grid, the idea is to connect the generation and consumption, transferring power where it's needed, and ensuring it's as cheap and efficient as possible, and reliable and resilient. That's why transformers play a fundamental role, because they will enable us to change the voltage, which therefore lowers the current and lowers then the transmission losses, energy conservation. So depending on the size of a PV plant in solar, we could interconnect directly to the grid at a medium voltage level or a high voltage level, and this typically depends from country to country or rules that are determined by the DSOs and TSOs. Perfect. Just wanted to give a little bit of context to everyone here today before we jump into the design of the transformers and the facilities inside RatedPower. We're going to start with the substation design. And I'd like to remind everyone of what a substation is. It's an installation, a facility that steps up the voltage from medium to high voltage level using transformers. There are typically three main types of substations: gas insulated substations, air insulated substations, and a mixed technology between the two. We attached here some pictures of each type, and inside RatedPower, we'll be working with air insulated substations, as you can see in this screenshot. This is also an image of the layout that we provide for the substation with some of its elements. For example, the MV switchgear, the transformer bay, the bus bars, and the output bays. All of these will be elements that will size either automatically and manually, and the idea of today is to learn how to do so. Similar picture, but in reality, right? Here we see these elements in a substation. And now let's find out how we design them in RatedPower. Another type of substation possible or available in RatedPower is what we call a pooling substation. And I mean, it's similar to a regular substation. The only difference is that it steps up the voltage from high voltage to extra high voltage level. And again, in RatedPower, only the air insulated substation type will be available. This helps us to connect or adapt our projects in a flexible way, creating different types of schema for the interconnection facilities and having a pooling substation that evacuates all of the generation. Before we jump into the tool, that's also going to happen today, I want to show you dynamically how to change these inputs. Just wanted to also show you how to do the sizing and defining different parameters within the tool. These are basically the four elements we'll be sizing: the substation arrangement, the transformer type, the transformer base size, and the output base. And the idea within RatedPower is that the tool will automatically size all of these elements according to a standard. We use the IEC and the IEEE standards, but the user can also size them manually with different parameters that they will find inside the tool. Let's start with the substation arrangement. And here we distinguish three types of arrangement: a single bus bar, a double bus bar, or a line to transformer, which requires no bus bars. For example, in the substation that I showed you earlier in this image, you see that we're using a double bus bar arrangement. RatedPower will automatically size the substation arrangement. This is something that if you want to learn in detail, I can refer to our methodologies, but basically we use a simplification method called the 2500 amperes method. I think it's interesting just for you to know how we automatically give you a recommendation. It will depend on from project to project, and that's the criteria used for that default value that you find in the tool. Besides the arrangement, we also have the option to customize, for example, the iron losses and copper losses, and the type of transformer. It can either be a 2-winding or a 3-winding transformer. Again, here RatedPower will recommend you the best choice based on the plant's capacity. Speaking now about, for example, the power transformer size, we have two ways or two strategies to define the size of the transformer. The user can either input the transformer capacity directly, and the tool will calculate the number of transformers required to evacuate the power of the project. Or you can input the number of bays, and then the rated power, the algorithm will do the opposite, which is determine the power transformer capacity, making sure that it withstands the flowing current with the protective equipment necessary. As you can see as well in this image, the short circuit impedance is also a parameter you can change, and it will play a role that I will explain a little bit later. Finally, the output bay number, and it concerns the number of outgoing bays from the substation to either the grid or the pooling substation. RatedPower also provides with a recommended value and as well as a minimum and a maximum for the protective equipment to be able to withstand the flowing current. Before we jump into the power station design, just wanted to take the opportunity to show all of these parameters in the context of the tool. What you're looking at right now is our interface, our design process interface, and all of these elements are found in the Green Point tab. As you can see, we can choose different standard. We can choose a different type of facility, but today's focus is on transformers, so we'll be focusing on substations. And this is also where you set the MV and the HV levels. After doing so, we find all of the options that I showed you earlier, the type of arrangements, the transformer losses, the number of windings, the capacity of the transformer, and even the output bay number. So this is where you will find these options in the tool that will enable you to manually define all of these elements and personalize your project and the documentation that we generate. Perfect. Let's now review the power station design. In this case, we'll be talking not about the high voltage stations, but about the medium voltage stations that also allocate a transformer. As we know, our modules generate electricity in low voltage in DC, and we need to step it up to medium voltage AC. The conversion to alternate currents can be done inside this skid or this transformer station or outside. That's depending on the choice of the type of inverter used. But a power station is exactly this, right? A transformer station that steps up from low to medium voltage. And again, the reason is to minimize the losses that occur when distributing the power and the electricity. In this image, you see a typical photo of a power station. And now we have also some options, for example, for defining the different parameters of the power stations within RatedPower. So you can see the MV level that I showed you earlier, the types of transformers of each power station type, number of windings, the capacity of each transformer, the short circuit impedance as well, the transformer losses, and the type of enclosure, if it's either indoor or outdoor. This won't have an impact in the model. It's just something that will be specified in the reports. Before jumping to the tool and to the optimization strategies, I just wanted to highlight an important concept in RatedPower, that is the types of power stations. We can distinguish between two types, the default ones, or main power stations. And these are the power stations that are prioritized in the plan with the algorithm installing as many as possible. Whereas the non-default power stations, also known as secondary ones, are installed when the remaining strings in an area are insufficient to connect a main power station, and then we define secondary ones, smaller power stations, to make use of these remaining strings and try to maximize the peak power of the project. These are also prioritized depending on their AC power, starting with the largest and moving to the smallest allowed. So if we go to the software, now instead of focusing on the grid point tab, we should go to equipment, power station, where we can set the size of our main power station depending on the number of primary inverters inside of connected to the same transformer, and secondary options that are smaller than the main one, right? Here you can see that if I enable my main block to be of 100 string inverters, all the secondary options will be the smaller ones, and I as a user can select which of these options I want to take into account. For each option selected, I can customize the transformer, the number of transformers, the capacity, the losses, and everything. So just bear in mind that this will play an important role when sizing the project. And this is exactly what we're going to be reviewing in this second half of the webinar, how to optimize your project. As I was referring in RatedPower, the smallest unit of AC power is the power station. Basically, the tool will only connect the structures when the size of a power station is achieved. That's why the non-default or secondary power stations could be very important in case the area is not big enough to fit a main power station. This could be the origin of some failed simulations or red structures that typically are linked to electrically disconnected reasons. And we're going to review some strategies to overcome these issues. Just wanted to remind everyone that the total AC power of the design will be the sum of all the installed power stations. And to address some of these issues, especially in smaller areas, we'll be modifying equipment or layout constraints. If it's a small area and we need to be able to fit a small power station, sometimes setbacks or the pitch distance or the structure configuration could be critical to finding that extra space that will enable us to install a smaller power station. Perfect. So how do we overcome these issues? And let me show you the first one. If we go to the tool, in this project, I'm going to use a string inverter. And let me define my main power station with a power of 33 megawatts of 100 inverters. I'm going to be rigid in this first simulation, and let's assume I do not want any other size other than the main one. What happens when I run the design? As you can see, in this project, we have two parcels, and the tool will only be able to fit one power station. We can see this by just looking at the final rated power of our project, 33, that's the exact amount of 100 inverters. But we see a lot of red structures. These are structures that physically can fit the area, but are not connected to our inverters, are not part of the layout, are not part of our project. How can we optimize this usage of the land? Well, in this case, this is a clear example of that prioritization algorithm. The tool is going to try to fit the main power station. It sees there is 15 or 16 megawatt of DC power remaining, but that is not enough to connect another power block of 33. Therefore, what it's going to do next is going to go through the list of secondary power stations, trying to find a smaller one that fits this remaining unused area. However, we haven't enabled one. We were a little bit rigid, and the tool only provides 33 megawatts of power. One of the strategies would be that, therefore, enabling several non-default power station options, giving the algorithm more flexibility to allocate smaller clusters of trackers or fixed structures do not meet the requirements of a bigger block. If I simply enable them all and I run the design again, we will see that it will now introduce a second power block, optimizing the usage of the area. While it simulates, I want to take advantage of this moment just to please ask you if you have any questions, leave them in the chat. We'll be having a Q&A after the presentation, and I'll be happy to answer to any questions you might have during this presentation. Well, perfect. Now it already simulated, and we can see how it's optimizing the project, inserting or installing this second power station, and now making the best use of the land and achieving a 46 megawatt rated power in this project. However, just wanted to highlight there are still some red structures in the design, and these are also removed by electrical configuration. But as you can see in this list, we enable all of the options. So what is the origin of these stress structures? In this case, it's linked to the DC-AC ratio. As you can see, this is the default value used when starting a design from scratch, 1.2, and it's somehow strict. These trackers, if they were connected, would be bypassing this 1.2 DC-AC ratio and therefore are rejected. So another strategy to optimize the project is to enable a button that we have created that's called Install Maximum Peak Power that optimizes the DC-AC ratio to connect the red structures. This option can be found in Layout, Power Requirements, Maximum Capacity, Install the Maximum Peak Power. As you can see, the tool will automatically give you a lower and upper limit for the DC-AC ratio at the inverter level. You can customize it. But the idea is that when I run the design, the software, the algorithm will still try to reach the 1.2 DC-AC ratio, but it will be able to accommodate those extra trackers, varying slightly the targets to maximize the peak power of the plant. And we can see that by just checking that the total unused peak power now is 0. Perfect. Another interesting fact is, for example, let me ungroup these areas and run the simulation again. In this project, we have 2 polygons. And unless I've done so, these polygons will not be connected in low voltage, which means I could have more power stations than needed in both areas. Another way to maximize or optimize the project in terms of the allocation of power stations is by grouping the multiple areas in low voltage. And this will enable structures from polygon 2 to be connected to a transformer in polygon 1, for example. To do so, the only thing I need to do is to click on this button on the top left part of the map, select the polygons that I want to group, and group them together. Now, when I run the design, the tool will automatically create the connections necessary to optimize the project, trying to install the main power station. As you can see, the difference with this simulation in regards to the previous one is that it wasn't installing the main power station. It was installing some of the non-default secondary ones. But now when I group them in low voltage, it can reach the 100 inverter block and utilize a smaller one for that part of the terrain. So this is a cool trick to have in mind when trying to customize multi-polygon areas, and it's important to connect them in low voltage. What about smaller areas? Again, we were saying these are more sensitive to layout parameters. In terms of distances, sometimes having space to fit extra structures could be critical to connecting smaller power station blocks, as we've seen. Therefore, minimizing setbacks or customizing the power station size, the power station location could be important. In order to do so, we'll be navigating through the Layout tab, and we'll find the different options in this section of the process. Of course, the pitch distance could be also an option, but it's not always a degree of freedom. But here in Power Station, you have the opportunity to locate it outside or inside the DC field. And this also is an important thing to review. Let me now change the location from outside the DC field to inside. And you will find that we can even gain a little bit of power sometimes. Basically, what happens is that the power station, instead of being allocated in the road, it will take the place of the near structure, the neighbor, minimizing the setbacks needed between the road and the power station and the structure. That's also another option that could be customized in the AA setbacks area, where you find different setbacks that you can minimize, trying to accommodate or gain that extra space to introduce smaller clusters of structures. Perfect. Now, before I move forward to a specific combination of power stations, I want to show you something that could happen with this prioritization algorithm. For example, instead of, at the moment, we've been working with maximum capacity. This is a strategy to size the PV plant, trying to fit as many structures as possible in the project. But we could work in specific capacity instead. In this type of strategy, we'll be telling the tool exactly how many inverters we want in our PV project, and the tool will only utilize the space necessary in order to do so. For example, if I run a design with 8 inverters, it will pick the power station of 8 inverters and efficiently only use that part of the polygon. Let me now change to a different project, different design. And I want to show you an issue that we could be facing. For example, if we have here, instead of a string inverter, let me change to a central inverter. And let's say I want a main power station of 8 inverters. If I target a group of 30 and I run the design, we will find that in the results, the design will only have 24 megawatts. Well, no, in this case, it's going to have 30 because I enabled the secondary power station, sorry, but we will see what happens. In order to achieve these 30 megawatts, again, just as a reminder, the tool will use 3 power stations of 8 inverters and 1 power station of 6. However, if I only want, for example, power station of 8 and 7, this could be a combination, right? If I have 2 of 8, that's 16, plus 2 of 7, that would be 30. If I run the design, the tool is also going to prioritize the main power station. It finds there's enough space to install 3 of the main blocks, but there's a 6 inverter remaining in the polygon. However, that option is not enabled, and we end up losing 6 megawatts of power. So how can I achieve a specific combination of 2 sizes bypassing the prioritization algorithm of the tool? This is something actually that we're developing and will be released in the near future. But in the meantime, we came up with a cool trick that allows to bypass this algorithm prioritization. This trick is only available for central inverters, for specific capacity designs where we're targeting a specific amount of inverters, and as a combination of 2 sizes. The idea here will be to enable secondary inverters and then size the design telling exactly the number of secondary power stations as the secondary inverters. So let me show you that with an example. If we go back to the same numbers, let's aim for 2 blocks of 8 inverters and 2 blocks of 7. And what we're going to do is define our main power station with 7 primary and 1 secondary inverter, and our secondary power station with only 7 primary inverters. if you look closely, this is the same as having 8 and 7, and we will find a way to tell that we want 2 of each kind. The main trick is the enabling of the secondary inverter and choosing the same inverter as the primary one. This is the cheating in the algorithm, where we can trick them to think they're different inverters, but in this case, it's the same one. Now, the definition of power station changes when we enable a secondary inverter, and here's where we say that we want our power station with 8, but in this case with 7 and 1. And then out of the non-default options, we will only select 7 and 0, this one. When I go back to layout, power requirement, specific capacity, basically here, what I say is I want 2 secondary inverters, 2 of those power stations of 7, and the 28 remaining ones will be primary ones. By doing so, you will see that we recovered the 30 megawatts goal while using 2 different sizes as a specific combination of power stations. This is a cool trick that we'll solve in the future to try to give more flexibility in the automation algorithm. But if you're curious and want to use this trick in your project, we also created an article, a step-by-step article in our help base that you will be able to find in the description of this webinar later. This is a generalized step-by-step where you can just input your desired combination and optimize your project. Perfect. Before wrapping up, I also wanted to take the chance to talk a little bit about the energy model, because when you look closely, you will find some losses related to the power station transformer. If we go back to the interface in the energy section, we see the iron and the copper loss. And this will be accounting for not only the power station transformer, but also the substation transformer. So where do we enable these losses? Again, let's go back to equipment, power station, transformer losses. These are the 2 inputs that the user has to define those 2 losses for the power station. And in the case of the substation, these losses will be, again, here in the substation transformer losses. If we want to look at the numbers and how we calculate the losses, we'd have to refer to the methodology of energy yield. And in section 9.2, you will find all of the formulas. For example, let's do an exercise with the iron loss for the power station. If we look closely, the formula takes into account the iron loss that we define in parts per 1, the percentage we put in the interface, and the capacity of the transformer. Going back to the tool, let me disable the substation transformer losses so we can only focus on the power station ones. And this will be the loss that we'll be looking at, 0.1. In this case, our transformer has a capacity of 8 megawatts, MVAs. And if I run the design and I check the documentation, we will find in the nighttime losses the exact number that is calculated using that formula. While we wait for this, I already ran the simulation earlier, so let me just open this file and open the energy yield results. It is an Excel file that, for example, in the first year hourly, we can check in the hours that we don't have any production, we have some nighttime losses associated with the transformer losses. This value, in this case, is exactly the 0.001 times 10. In this design, the transformer was at 10 MVA times 1 million, 10,000, which is approximately the same value we find here. So that is just a quick way to double check how those numbers impact your energy yield results. And we could do the same exercise, for example, for the substation ones or for the copper losses. In any case, I recommend everyone to try to play a little bit with these parameters. And if you have any questions, don't hesitate to reach out to us. We'll be happy to take a look and try to trace back the origin of these results. Another important aspect of those losses is that they do not only play a role in the energy model, but they also impact the grid requirement calculation of the power factor. This is why defining the strategy setting is so important, because depending on where we place the point of measurement, we'll be taking one loss or the other into account, or both. No? For example, if I place it in the output of the substation, the tool will calculate the power factor at the inverter output, taking into account both losses, the power station and the substation ones. However, just check how this number is going to change when I move the point of measurement to the substation input. Now the losses in this case remain the same because I had disabled these losses, sorry, but once I enable them again and I do the same exercise, you will see that it varies. There you go. So it also plays a role here in the power factor calculation. And something to bear in mind is that it's not the same disabling the losses or putting them to zero. This could have the same impact for the energy model, but it will not have the same impact in the reactive power. And before wrapping up, just a little bit about the documents. We've been speaking a lot about transformers, losses. Where do we find these things? So I wanted to highlight some of the main documentation that is related to this topic. Obviously, the reports that describe specifically how we size things, both in the design, the energy, or the substation. The bill of quantity will highlight all of the elements and the sizing that we see in the algorithm. We can also find different SLDs for the MV, for the LV level, or for the substation, and also a substation of the layout of the substation as the one I showed earlier with the different elements highlighted. We just opened the energy yield results, so that I think that was a cool exercise to trace back that nighttime loss related to the transformer of the power station. And besides all of this documentation, I also like to highlight that we provide a power flow model, so you can take the work that you perform here at RatedPower to other tools like PSSE or DigiSilent. Well, that was all. I hope you liked the presentation and you find these tricks interesting and useful in your future designs. And before finalizing, I wanted to also answer some questions, so I'm going to be reviewing some of the questions that you left in the chat. I'll try to do my best, and if we don't have time for them all, I'll make sure we reply via email after today's session. Thank you so much. Perfect. So I see here, for example, a question that says, does RatedPower take into account the BESS when sizing the transformer of the substation? And yes, it does. That's a great question. I think in this project, I had disabled the BESS. So for example, we're using a 10 megawatts. This PV project only has 10 megawatts. And if we come here to the substation section, our transformer capacity is of 45. I believe that's because I had defined it manually. I can change this value to 10, or better, let me just disable it and see what it does automatically. Given the PV plant is about a 10 megawatt plant, in this case, it's choosing a transformer of 10 megawatts. This is without BESS. So let's see what happens when I enable a BESS system. In this case, we have a BESS of about 22 megawatts. So if I run the design again, we will find that now the substation transformer has a bigger capacity Therefore, yes, it does take into account the storage system when sizing the transformer of the substation because it needs to evacuate all of the power. And this is an example for this type of schema, for example, with the substation and the battery area connected to this one. But as you may recall, last year we released the flexible interconnection schema where we can have different types of substations, switching and breaking stations, or pooling substations. And you could even have one of the substations evacuate all of the power of the BESS, while the other one's evacuating the PV power. Thank you for your question. Perfect. Let me find another question here. Okay, so this must come from a user. It says, how can I have a bigger substation transformer size than what the drop-down list shows? That's a great question, because if you recall, when we were sizing here the project in grid points, there is, in the capacity of the transformer, there is a drop-down list. So how can I get more options than the ones shown in this list? This depends on two parameters. One is the short circuit impedance. Just let's see that the maximum value in this dropdown right now is 65 MVAs. If I double, for example, the impedance, you will find that now we can go up to 130. So it depends on the short circuit impedance and also on the MV level. If I double the MV level as well, you will find now that this drop-down list has increased even more. So by changing those two parameters, you could impact the options shown on the drop-down list. In any case, if you don't find a specific transformer size, or if you're having any issues trying to get to a specific configuration, please reach out to the customer success team and the support team, and we'll be happy to take a look at it. Thanks for your question as well. Let me find here, for example, okay, we have a question that asks, is it possible to export the project, including the substation, to PF Ditch Silent? And yes, exactly. That's what I was aiming to highlight with the documentation section. You have here some raw files that you could utilize to import into those programs, PSIC or Ditch Silent. And if you have any doubts as well, please reach out to us, or I believe we have some article on how to include those in the program. So you can find those resources on our help center. Let me find another question. I think we have time for one more. Could the slides be provided? Yes, we'll be sending the slides afterwards. And finally, does the software take into account different manufacturers regarding the MV power stations, as it will affect layout due to different sizes? That is an amazing question. As you know, the philosophy of us as a company and as a software provider is to make the user's life as easy as possible. And that's why we always have some sort of library or public databases for the PV equipment, module, inverter, structure. We also provide topography sources or medial sources. However, for the power stations, we haven't found a way to establish or create a library the same way we create a library for the module or the inverter. This is related to the fact that these products are not standardized in the same way as the modules are, for example. So our approach is more agnostic in this sense. You can size the different elements in a more generic way, trying to replicate the data sheet of a specific manufacturer. So by changing the number of primary inverters, you could aim for a specific configuration. For example, I know that Huawei has, for example, different solutions that could have the 330 in clusters of 20, but maybe you also want to consider the options with 19 and 18. Here, the important part would be to also keep the same capacity of the transformer. So I recommend going through these options and changing the capacity of the transformer of the power station to ensure it's the same one is used afterwards and we find the same one in the bill of quantities. Regarding the sizes, the physical dimensions of the power station, you can change those here in layout, power station, dimensions. So I believe you'll have the tools you need to replicate a specific product. And if you're having any complications or issues, please also reach out to us and we'll try to make the best as possible, trying to help you. And well, thank you everyone for all of your questions. There's a lot more that weren't answered, and I'll make sure to answer those afterwards via email. And I hope you like this presentation. If you have any questions, you can reach out to me. This is my email. I'll be happy to help you or guide you through more optimization techniques. And thank you for your time and interest. Have a great day and see you on the next one.